Okay, let's go and get started today. And I'm just going to jump right into things because we have a little bit of stuff that I want to cover today. This is kind of a continuation of the review that we have been doing. And I'm going to add maybe some stuff you haven't seen before in today as well. So we're going to start combining the trigonometry, object-oriented programming, lists of things together for this class. And today I'm going to do a little bit more stuff with trig as well and talk about how to use other ways to use trigonometry to do some things with vectors and forces. And then we're also going to get into a little bit of simulation using those. In other words, like some physics kinds of things using those. So let's go ahead and get started. All right, so first off, review of trigonometry for radians. We've done this several times now, but it's important that you understand that. So radians are the mathematically natural way to measure angles. The reason being that if you have a circle with a radius of 1 unit, so let's say this is 1 inch from the center of that to the outside edge here. So it's 1 inch from there to there. Then what's the distance all the way around? Well, 1 inch radius means 2 inch diameter. And then if you then measure the distance all the way around, then it's going to be 2 pi or 2 inches or 2 pi inches all the way around. And that's true no matter how big the circle is. One radius, no matter how big that radius is, will fit 2 pi times around the outside. So as we walk around the circle, we could think of that as an angle. So maybe over here on the side, that would be 0 degrees. We haven't walked anywhere. That's where we started. And if I had a little Sharpie, I could make a mark on this thing and then we could draw it. But as we walk around this way and we get to there, that's, well, if we walked all the way around, it would be 2 pi. Halfway around is pi. Quarter of the way around is pi over 2. Eighth of the way around is pi over 2, so pi over 4, and so forth. 1 degree walking around would be pi over 180, and so forth. So the idea there is that it's just how far as we walk around the circle. So now today's agenda, we're going to use that stuff that we just looked at over here, use that trigonometry stuff. We're going to do a little more review of that. We're going to dig into trigonometry for vector-based drawing, so to draw things at different angles. We're also going to use it for computing and force vectors and applying them to a motion vector. And then we're going to use that for some physics simulation. And essentially, this is going to prepare us for implementing some cool particle effects stuff in next class. And it's also going to prepare us for doing some really cool effects things in the games, our games that are not particle effects. And we're also going to have our first lab next time as well. So make sure you go over this. You might want to follow along when I do the programming. You can always pause the video, write some code, look at what's on my screen, make sure that you follow what I'm doing and understand why I'm doing it. Write your code, unpause it. Or you could watch the whole video all the way through and then try to write it yourself and then go back and look at it. It's really whatever works best for you. But you should probably write some code and try to follow along either before or after we go through this stuff. All right, so here, back to radians for a second. Those slides probably should have been in the other order. But here's our circle, 0 degrees or 360 degrees gets us back to the same place, and that's either 0 or 2 pi radians. Halfway around the circle, pi. Quarter around the circle, pi over 2. And so forth, and you can see all those there. And for conversion purposes, again, if it's 180 degrees to get halfway around, and that's pi, then 1 degree is equal to pi over 180 radians. Or 1 radian is 180 degrees over pi degrees, or 57.2958 degrees. All right, now, sine and cosine, quick review of that. If as we're walking around the outside of the circle, we only focus on how far above or below the line we are, and how long that is with that radius of 1, then it would range from 0 when we're on the line, 1 when we're as far as we can get above the line, and as we keep walking, it'll go back down to 0, and as we keep walking, it'll go back or all the way down to -1, and then it'll head back to 0. And that's what sine is. So sine is how far above or below that line we are. Looking at this triangle, it's this dotted line here that's labeled sine there. So as we walk around, here's 0. As we walk on, the red is sine. So it increases up to 1, it decreases back to 0, goes down to -1, and then back to 0 when we're at 2 pi or 360 degrees. And that makes sense. Now cosine is just, rather than looking at up and down, it's looking at left and right. How far over are we? So when we start, we're at 1 over. It shrinks back down to 0, and you can see that here. Starts at 1 over, shrinks back down to 0, goes all the way over to the left where it's -1, and then goes back to 0 again. And then when we're back where we started, back at 0, we're all the way back at 1 again. So you can see that this length of that line, or that bottom leg of that triangle, all the way up here. And then it will shrink, 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 shrink all the way to 0, and then it'll go negative and go all the way to -1, and then it'll go back to there. So that's what sine and cosine are, and we're going to use those. We've used those before, so this is all still review. Now, what we're going to do today is, first off, we want to draw like this spaceship shape like that. And we might think of that as, this is the ship's X and Y position, and we could do this in an object. We could make a ship class that draws this thing. But if we think about the points that would connect the dots to make this shape with a polygon, we might think, well, this point here is one of the points, and that, and that, and that. That's a polygon with 4 points. 1, 2, 3, 4, and then back to 1 again. So with those 4 points, we might think of those as having their own X and Y values. So this would be, point 1 would be P1X, Y, P2X and Y, P3X and Y, P4X and Y, and then back to there again. Now, the idea there is you might think about those different points going around that ship as having an offset from the ship's X and Y. So now in this case, notice P1X is going to be some number forward or to the right of X, so ship X plus 30, and P1Y is along the same Y as ship Y. And then this one up here would be some over to the left, 15 to the left in this case, and 10 up. And P3 is none of them up and down, so Y is the same, but X is maybe -10, and so forth. But the problem with that is, if I just tried to hard code it like that, what if I wanted the ship to rotate? What if I don't want it to always be facing this way, but I want it to sometimes be at different angles? Maybe sometimes at 90, facing up, sometimes maybe at 45, maybe sometimes at like 10 degrees or 1 degree. So we want to be able to have that ship have the ability to rotate and still be drawn and still have that same shape as we rotate that around. So the way we're going to do that is we're still going to use these 4 points, P1, P2, P3, P4, but we're going to think of them a little bit differently. We're going to think of them as being a certain distance away from the center of the ship, but at some particular angle, the angle that the ship is facing. So in other words, how it's drawn here, that might be like 40 degrees or something up to there, from 0 degrees being directly to the right. All right, so that P1, when it's that way, is whatever the ship angle is at plus 0 degrees from the ship angle. It's the same angle as the ship. But P2, we might think of that's 120 degrees from our ship angle. So ship angle plus 120 degrees, and maybe 20 units away rather than 30 units away. P3 is going to be a shorter number of units away, maybe 10 units away at 180 degrees. P4 would be just like P2 is 120 this way, this is 120 that way, and the same number of units away, 20 away. So think of those points as offsets from the direction the ship is placing, and a length away is going to help us calculate those points. So here's what we're going to do. We're going to use sine and cosine on the angles, because that's what sine and cosine will give us. So if we think of those as a triangle that makes this over here, like this triangle there with that being 120 degrees, then we could actually compute how much is the dx, how much is the dy. So dx left and right, dy up and down. How much of that do we need to get to that particular position given the angle that we're at? And once I've computed all the x's and y's for all of those points, P1, P2, P3, and P4, I just connect the dots with a polygon to draw the shape. Okay, so here's essentially what we're doing. We're saying, okay, take the ship x and add 30 times the cosine of the angle to get to P1y. Same thing here, 30 times that. And you'll notice that I have these inverted. These are minus here because of that -1 times that for the flipping the coordinate system, just like we've done on all the other things. But notice here's the distance away, and here's the angle as an offset from the angle of the ship itself. So P1 is always directly in front of the ship. So if it would help you, you could think of this as angle plus 0, angle plus 0. But then P2 is the angle of the ship plus 120. And P3 is angle of the ship plus 180, so directly behind us. And then P4 is angle of the ship minus 120, going back this way to get to that. And then these distances here, the lengths of these lines we have drawn over there. So after we computed those, we would just connect the dots to make a polygon, like that. Okay, so that's the basic idea of what we're going to do. And before we switch over and write some code that does that, a couple things to consider. The math module uses radians. Back over here, we were using degrees to represent these. And I think I switched from 120 to 130. I don't know why. Maybe 130 looked better. But really, we can play around with these distances, play around with these angles to really get any shape we want out from that polygon. So the y values were negative due to the inverted y-axis. That's why these have minus signs instead of plus signs. And really, you can make any shape you want using that method. So if you want to have a little rotating star, or you want to have a square, or you want to have, I don't know, something that looks like a moon shape, you could actually just connect the dots to make any of those shapes that you want. All right, so let's actually write the code to draw that. And I'm going to do this in an object-oriented way in my code, but we're going to have this draw ship method. It's going to use the angle, but let's make a simple program to test this out. So I'm going to switch over to Python here, so give me just a second. And I'll switch that over so you can see what I'm doing here. And we're just going to throw this together quickly just to draw that ship. So let me, here, hold on 1 second. I'll switch it so you can see what I'm doing. Okay, so here's my program editing window. And I'm going to give this a comment and like vector based drawing of a ship. Okay, so in this case, I'll import Pygame, I'll import math, pygame.init, display surface equal pygame.display.set mode, and we'll make the screen 800 by 600. And now we'll have our game loop while true. Let's do pygame.event.pump. So the program will pull in any events that are in the event queue. Now we'll get the keys. Keys equal pygame.key.get pressed. And then if keys pygame.k underscore escape. So if they press the escape key, then we'll break out of the loop. At the bottom of our loop, we'll do a pygame.display.update so we can see any changes we make. And then after the loop, we'll close the window. So pygame.display.quit. All right, and this is code that we've seen a lot of times. There's one other thing that I'm going to start adding to these, and that's to limit our frame rate to some constant thing so we're not running too fast here. So what I'm going to do here to limit my frame rate, I'm going to make a FPS clock equal pygame.clock or .time.clock. So that makes a clock object. And then at the top of my event queue, I'm going to say FPS clock.tick. And we're going to tick that at 120 hertz. So we're going to have 120 hertz frame rate for our main loop here. Now, before I do anything else, let's run this. So let's do a F5 to run that. And when you run this, I'm just going to give this a name. I'll call it rotating ship.py. And we don't have the ship drawn yet or anything like that. And I did something wrong because it crashed. Let's see what happened. Oh, I just had a typo. There. All right, let's try again. So there's the screen. We hit escape. It closes. So we're all good. So now we're ready to actually start writing our code for our ship. So I'm going to go ahead and make this a ship object up here. So I'm going to say class ship. And we'll put object here in parentheses. And now let's make our constructor. And for the constructor, we could have parameters in here to say where we want it to be start out at, but I'm just going to put it right in the middle of the screen. So I'm going to say self.x equal 400, self.y equal 300, self.angle, and this is the angle that it's facing. So I'm going to call it angle underscore facing. And I'm going to make it 0, so it's going to be facing to the right. Eventually, we might want to have it move. So I'm going to say speed. I'm going to start out as a speed of 0 for right now. And notice now we have an X and a Y position, an angle, and the speed we're not really going to worry about too much right now. We'll maybe adjust that here in a little bit for the second half of this. And in fact, we could probably leave that off for now. So if you want to just save some time writing it, leave it off for now. We'll add it in later when we go to make the ship move. So here, let's do a def render to draw the ship. And to draw the ship, as a reminder, what we want to do is we want to calculate all 4 of those points, P1x, P1y, P2x, P2y, and so forth. And then we want to connect the dots of those with a polygon. So here, I'm going to say self dot. And what I want to do here for rendering this is, well, let's leave that up for now. We don't need those to be self. So let's just do P1x equal P2 or P1y equal. So we now know we need to calculate each of these positions. So each of the positions that we have for the P1x and P1y, this is going to be self.x plus. Now this is x, so that's going to be math dot. Now x is left and right, so that's cosine. And then we're going to convert to radians, self.angle facing. Now, P1.1 was the one directly in front. So really, we could say plus 0 in there if we wanted to, or we could just leave that off. I'm going to go ahead and put it in there for symmetry with the other ones here. But that's what we want. So that's giving me, but cosine, remember, gives a value between 0 and 1. So we want to plug that in. I believe we had 30 here. So 30 times that. So this will give me a value of 30, or it'll give me a value smaller than that. Now, there's one other thing we're going to have to do later. We'll see what we need to do in a little bit. Now, let's do the same thing for P1y. And that's the same, just the y part of this, the up and down part of this. So this is going to be all the same, except this is going to be sine. And there is one other thing we need to do. Remember, this needs to be negative, so you can do negative 1 times that. Or we could just put minus 30 times that there. And this needs to be y. All right, so that's 0.1y. That's the one that's directly in front of the nose, 30 pixels in front of the nose. And I believe what we did next was we then had 20. And this is all the same. But now, rather than this being plus 100, this was 120. 120. So notice that this is just a new point. It changes to P2. 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 So point 2 is now 20 units away from the center of our ship at an angle of the angle we're facing plus 120 degrees. In other words, plus 120 degrees this way, all the way around facing backwards. Now we're going to do the same thing for point 3 and point 4. So I'm just going to go and copy these here real quick. Point 4, we know what that's going to look like. That's also 20 units away, but at the angle we're facing minus 120. So off the, what's that, the starboard side instead of the port side, 120 degrees off the other side. And now point 3, remember that was 180. And I don't remember what we had for this, but we'll do 5. And we can change the points around later on. All right, so there are all the points. Now we just need to make a polygon out of that. All right, so display surface dot draw dot polygon. And the polygon we're going to just, or actually that's not how that works. It's a pygame dot draw dot polygon. Wrong graphics library. And this is onto the display surface, a color. Let's make it kind of a bluish color. Now the next thing we need here is going to be my point list. So that point list, in this case, I'm going to make a list. My list of points is going to be P1x, P1y. And then we're going to need P2, P2x, P2y, P3, and then finally P4, x and y. That's the end of my list, and we want this to be solid and filled in, so I'm going to put a 0 there. All right, so that's going to draw it. So let's go ahead and, now this is just a class, so we aren't going to see anything drawn if we run this, so we need to make an instance of that. So I'm going to make an instance of that. We'll put it up here and say player ship equal ship. So there's my ship class. And then in my code down here, I'm going to clear the screen. So display surface.fill with the color black. And then I'm going to do player ship dot render to render it. Now let's go and run this. And I think I screwed up my list up here. Let me look. I'm missing a parenthesis at the end. There we go. Okay, now there's my ship, but on the screen. But you'll notice that with that ship on the screen, it's not. I don't have anything in there to rotate it yet. So let's make it so we can rotate that. And also you'll notice we're getting this warning about us giving floats for these points. That's the other thing I mentioned that we should probably do. And in this render, one of the things that I'm going to do here is, oops, that's the wrong code, hold on. One of the things that I want to do here is make integers out of all of these. So one of the things we could do to do that is I'm just going to put int on all of these when we compute it. And then we won't get that stupid warning. We could put them on that. I don't know why Pygame did not just build that into the function. Since there is no fractional pixels, like just ignore the floating point part and save all of this extra coding we have to do out here. Older versions that actually did that, I have no idea why they removed that. Doesn't make sense to me. But anyway, there we go. No more warning. There's our ship. Now let's make it rotate. And actually there's one other thing I want to do here, and that is I think it would look cooler to have, rather than the whole thing being a solid color, I want to have one side a little bit darker than the other. So I'm going to actually do this with 2 polygons. I'm going to do one with 0.1, 0.2, and 0.3. Like that. And I'm going to do the other one. So I'm basically getting 2 triangles here. And the other one I'm going to do, we'll make this one a little bit darker. Let's do, instead of 200, we'll do 150, 150, 200. We can play around with the colors later. But this is going to be 0.1, 0.4, and 0.3. So let's see if that looks better, and then we'll make it so we can rotate the thing. Okay, that does not look better. What did I do wrong there? 1, oh, I see what I did wrong. 4, 3. Okay. So there we go. You can kind of see the 2-tone effect going on that we're looking for. One side lighter than the other. Now let's make that thing rotate based on key presses. Now, since we did this with a with kind of a class, really what we need to do to change it is the angle facing. So what I'm going to do is I'm just going to add a couple methods here. So def rotate left. And let's call it, instead of left, let's call it clockwise. That probably makes more sense. And I'm going to make an optional parameter here that's amount, but I'm going to make it so if we don't specify the amount, it'll be 1. And we can play with that later on. So inside of here, all we need to do is say self.angle facing. Now this is clockwise, so that's going to be decreasing the angle facing minus equal amount. And then we'll do the same thing for counterclockwise, but we'll add the amount. Now let's add some code to actually be able to rotate that. So up here in my code, I'm going to say if keys, and we're just going to use the A and the D keys for this. So pygame.k_A. So if we press the A key, that should go counterclockwise. So this is going to be player ship dot. Now remember, that's going to be that method up here, rotate underscore CCW. So let's write that. So rotate underscore CCW. That's a method. Now let's add that same code, but we're going to rotate clockwise if we press the D key. Let's run it. Oh, I screwed up when I wrote those methods. I forgot to add the self at the front of those. All right, here. Self, comma. Self, comma. All right, now we should be good. All right, so there's the screen, and I press the A key and it rotates counterclockwise. I press the D key, it rotates clockwise. And just to show that in a little more detail, let's make the ship a little bit bigger here. And really, I could do here. Let's do this. Self.scale factor equal 1.0. So we could actually have the ship have a scale factor here, and then I'm going to do here this 30. I'm going to multiply it by that. So self.scale factor times that. And I'm going to do that on all these. So in other words, we're scaling up the distance away from the center by the scale factor. If it's 1.0, we'll get 30, 20, 5, and 20 for all of these. But if I make it 2.0, so this should work the same as it did before, but now we have that scale factor in there. But now I could actually make the ship bigger if I wanted to. So I'm going to do a scale factor of 2. And now you'll notice the ship will be twice as big. But it still rotates. Okay, so that's what we wanted it to do. And if we want it to rotate faster, when we call the rotate on that, we could just change the amount or change the default amount here. Make this like 3. Now it'll rotate 3 times as fast. Although apparently that's asymmetrical, so let me look at that. Oh, I only changed it on 1. There we go. So now we have this spaceship that we can rotate at an angle. And notice it's rotating around that point right about there. So 5 away from the tail, 30 away from the nose. And if we wanted to change the geometry, we certainly could. It would just involve drawing a different thing. If we wanted more points or less points, or we wanted like a little circle that represents like the center of the ship there to be drawn, we can certainly do that. But that's the basic idea of what we're doing there. So let's look at that code one more time to get a feel for what we're doing there for the actual drawing of that based on the vectors. So in other words, we're thinking of each of the points as a certain distance away at a certain angle relative to the angle that the thing is, the front angle that we have. So in other words, if you think about this is straight in front of me, then think about how far away that point would be and at what angle off of the nose of the ship would it be to get to that point that I want to draw. And we just do that for all these points, and then we just draw the shapes of those later on. Okay, let's switch back to the slides for a second. And we're going to come back to this code and add some other stuff to it in a little bit. So here, back to the code, we did that. That's all good. Now, the second thing that I want to do today is use trigonometry for another purpose. And that other purpose is adding like a thrust force to our ship. So we want it so we can actually make that ship so that we can, like, for example, press the space bar, thrust will come out of the back, and then you'll see the ship kind of get pushed in a direction. So we want to be able to apply a force to the ship. So to do that, we need to be able to add a force to the ship and have it result in a change in the speed and direction of that ship to make it move. So how can we apply a force to that? Now, that's going to be just some other trigonometry. And we're going to use that for some physics simulation. And in this case, what we're doing is we're dealing with, if we think about Newton's first law of motion, basically it's an object will remain at rest or in uniform motion in a straight line unless it's acted upon by some external force. So without force, an object will continue to move in a uniform direction at a uniform speed. It will not change its motion unless some force acts upon it. All right, so with a force, an object will have some sort of changing direction speed. So without a force, it won't. It'll continue along that straight path. But if a force comes and acts on it, it'll change the direction of that thing as it's moving. All right, so in other words, here's Newton's first law. Here's our ship. There's the vector that's going to have a dx and a dy. And then if we think about that as a triangle, without any force, we just repeat that triangle the next time period, and it'll get us to a new place. So going through that, we can compute dx and dy. We know how to do that by using an angle and its speed as the hypotenuse. We can get the x component of that and the y component of the x displacement and the y displacement. So the next frame of the motion, it would be just applying that x and y again. They wouldn't change. It's uniform. There's no force acting on it. It'll just continue to move how it had previously. Same dx, dy, applied again and again and again. But imagine that we have a force acting on it. So let's say gravity. There's a slight downward force pulling the ship downwards or towards the center of some planet. So what happens to this motion that was going to be like that? Well, with that force acting down on it, we basically just need to apply that force, which is just another little, I can think of it as another triangle. It's a force acting at some magnitude in some direction, in this case downwards. And notice that's going to create a new motion vector that is now different than the one it would have been because we had that little bit of force tugging down on it. So rather than it going up here where it would have gone when we apply this force to it, it's now going a little bit slower, and it's going at a slightly different angle, this blue one here. So that's the way that forces are going to act on things. We're going to take the motion vector of the object. We're going to apply the gravity vector in this case, or the force vector, to it, and that's going to produce this new vector, which we're going to call the resultant vector. And essentially doing that over and over and over again at each step. So notice the force is the same for each step. The little orange arrow here is the same. But what you're going to get is this complex thing when gravity is acting on this, that when you move that thing, it travels in kind of this curved path. And as it was going up, it kind of slows down, it evens out, and then it starts to accelerate going downward. So we can really add any force in that way, and you can actually see that happen here. So here's this ball, and the frame rate of the camera I have is a little bit slow on this laptop, but I don't know if you can see that, but actually maybe the blur helps. But you get kind of that curved path. Oops, I lost it. My table tennis ball here. You get that curved path, and that's because there's a force acting on this, pulling it downwards, affecting what would have been a straight line otherwise. Now, you can apply other forces to this as well. Like if I, for example, I tap it on the bottom, that's a force impulse going up. Oop, I screwed that up. But it would jump up out of my hand. If I take it and I apply force with my hand and hit it, it'll apply a force vector, a large force vector in the direction that it was struck. Okay, so the idea here is we can also use that to add something like a thrust force. So if the ship is facing in that downward direction like that at that angle, and we apply thrust, there's the thrust force being applied to, and if it's moving in that motion vector kind of to the side like that, and we apply a thrust this way, then we should see it start to move in a different direction. And how do we apply that thrust force, or how do we apply any force vector? Well, it has its own dx and dy. We just basically, to come up with a new position of the resultant vector, we take the dx of the ship, its motion vector, the dx of the force vector, in this case, f underscore dx. We add those together. That'll get us to this point here. We take the dy of this, the force dy of that, add them together. We get that point there. So the resultant dx is the motion dx plus force dx, resultant dy, motion dy plus force dy. We add those together, and that gives us our resultant, which has this resultant dx, resultant dy that comes out of that. Now, that is going to be used to compute a new speed and angle. So the new speed and angle, here's the new angle. The new speed is the length of the hypotenuse. We looked at how to do that last time. So basically, computing the new speed and direction, we use a Pythagorean theorem to get the new speed and the new angle of travel. We're going to use the arctangent 2 to get the angle for that. So here's the kind of code that we're going to be using to do that. So notice it's just sine and cosine to get the dx's and dy's for both the motion vector and the force. We add them together over here to get the new dx and dy, and then we use the new dx and dy to compute the new speed of the ship, the new angle of travel of the ship. So basically just like we had back here. All right, so let's add that code to our spaceship to be able to have it move and thrust and kind of fly around on the screen. So I'm going to switch back to Python here for a second. So give me 1 second to do that. There we go. So this is the same code we had before. And as a reminder, what this code does, there's our ship. There it is at different angles. I'm a little unhappy with how big it is. It's probably a little bit too big. So I'm going to go and reduce the size back down from that for scale factor of 1 again. All right, so there's my ship. There it is at different angles. Now I want to make it so that when I, actually I'm going to press W to thrust. So when I press W, I want that to apply a force to that. Okay, so how am I going to do this? So the first thing I'm going to have in my code here is, instead of an angle facing, I also want to have an angle of travel, self.angle travel, or angle motion. We'll start them out both being the same right now. But what we want to do, and the reason we're decoupling those is because we're going to apply the force in the direction it's facing, but it's going to be moving, it can be moving independent of that, because we're not going to have any friction or anything in this universe. It's just going to kind of fly around on the screen. So, but down here, I'm going to go ahead and make a move method. So def move the ship. So to move the ship, I'm basically just going to use the compute the dx and dy at the angle that it's moving. And here, let me move this up here so you can see all of it together. I'm going to put it right there. All right, so essentially what we're going to do is I'm going to say my dx and my dy. So to compute those, this is going to be, and we're also going to need the ship's speed. So let's give it a speed. So self.speed. We'll start it out as not moving. So what I'm going to do here is say self.speed equal, or times, So that's again, that's the hypotenuse of that triangle. We're going to scale that up from math dot, this is x, so it's cosine. And here we're going to do math dot radians of self dot. Now this is how it's moving. So this is the angle of travel, not the angle it's facing. So self dot angle travel. We're going to do the same thing down here, but we're going to put sine. And then we need our -1 on this, so -1 times all that. So there's my dx and my dy. Now we're going to move the ship by that amount. So here I'm going to say self dot x plus equal dx, self dot y plus equal dy. Now notice we could have done that all in one step and just said self dot x plus equal this whole thing. But for clarity, we'll just divide it up so you can see what we're doing. We're computing the dx of the motion vector, computing the dy of the motion vector, and then we're applying them to the current position to get the next position. Now, we've got that to move it. Now, there is one other thing we probably ought to do. Let's make it wrap around on the screen, because the way it is right now, if we drive it off the screen, it's gone. So let's say if self.x ever gets to be greater than 799, then self.x. We could say equals 0, but I'm going to say self.x minus equals 799. Or let's say minus equal 800. Now let's just set it equal to 0. We've done that before. That's a little bit unrealistic because if we're going really fast and it goes off, it'll come right on the edge rather than being partway in. But we're going to do it that way. And we need to do the same thing with what happens if self.x gets to be less than 0. We'll set it equal to 799. And we need to, there's another way to do this as well. But now let's also wrap this thing around the y-axis. So self.y greater than 599, self.y equals 0, self.y less than 0, self.y equal 599. So now we're wrapping it around on the screen. Okay, so now we have that, but we don't have a way to apply a force yet. So let's add a way to apply a force. So here, def apply force. And to apply this force, what I'm going to do with this method for applying the force, I need to know what the magnitude of that force is. So what's the amount of the force and what's the angle of the force. So let me do F underscore amount to make this a little more clear. Force angle. Now, if we wanted to, this will apply any kind of generic force at any angle of any amount. We could also make a function that's just called apply thrust, which is always going to be the direction the ship is facing and always some fixed amount. But for right now, let's go ahead and do this with this apply force this way. And then we'll add the thrust thing in a second, which will apply the force for us. So here, so this is more of a generic way to apply a force. What I'm going to do here is I'm going to say, first we need to compute the f dx and f dy. So we already know how to do that. That's similar to what we did up here. So f dx is going to be the force amount times math.cosine of the angle. So that amount at that angle is the dx. The dy is going to be the same thing, but this is going to be sine. And we need our -1. Now, to apply that force, we are now going to add that to our dx and dy from this. So we need to calculate these again down here. So this is the force dx and dy. There's a motion dx and dy. Let me just switch the order of these to make it match what we had in the slides. And now we're ready to add those. So resultant dx is going to be dx plus force, or f dx. And our resultant dy is going to be dy plus force dy. And now we need to compute back to the new speed and angle that results after applying that force. So here, self.speed and self.angle. And the angle that we want here is going to be the angle that it's traveling. So angle underscore travel. Doesn't change the way it's facing to add a force, only the way it's travel. So angle underscore travel. All right, now if you remember how we compute those, the speed, we just use Pythagorean theorem on this triangle. This dx, dy, those are the two legs of the triangle. We just need the hypotenuse of it. So to do that, we're going to say resultant dx squared plus resultant dy squared, that whole thing, square root of that by raising to the 0.5. There's my speed. Now the angle of travel, we said we're going to use math.atan2 for that. We're going to say minus resultant dy dx. And again, the reason this is minus is because of that inverted coordinate system. We had to invert back to get that angle. Now remember, math.atan2 returns radians. We've been storing everything in degrees, so let's just convert it back to degrees here. So math.degrees. Okay, now we have our new speed and our new angle after that force is applied. Now, let's actually test this. So down here, to apply a force, I'm going to say if keys pygame.k underscore, and I said w will apply a force in the forward direction. Player ship dot. Now the thing that we want to have here is going to be, this is going to be the thing that's applying the force. So apply force. And remember what we need to pass to that was the, looking back up here, was the amount of the force and the angle that we're applying it. So the angle here, we're going to actually extract this out in a second, but the amount, let's make it a really small force. Let's do 0.01. And let's make it the direction. It's going to be player ship dot angle facing. All right, let's try that and see what happens. And for some reason, nothing's happening. Hold on. That looks okay. Let me make that a little bit higher force and make sure it's still not doing anything. Okay, so for some reason we're still stuck there. So let me take a look at my code and see what's going wrong here. And let me temporarily just add something in here and see if we're actually getting a dx and a dy in here. Okay, so we are getting dx and dy. And those do seem to be changing. Let me look at my, where, am I actually, oh, I know what the problem is. I'm never calling move. So I'm doing everything, but I need to, in here, call player ship.move. All right, so simple error. We left out the thing that actually moves the ship. But our application of force seemed correct, so let's take that. Let's take this back out. And then let's come down here. And let's lower that force amount again because 1 is way too high. So 0.01. All right. So there's my code. I apply a force. It starts moving in the direction that I'm applying the force. Now, one thing that I don't like is we can't see it thrusting. And the other thing I don't like is that it's a little bit hokey to me to have to pass in the angle we're facing here when we just want to have the ship thrust. So what I'm going to do is I'm going to come up here, and I'm going to make another method. I'm going to call it thrust self. And the thruster is whatever amount it is, so I'm just going to have it call that apply force for us here. So I'm just going to call self, or I'm just going to say self dot apply force. And in here, I'm going to pass in my amount 0.01 and my angle self dot angle facing. So now in my code down here, I can just call ship.thrust, and that will call that for me. So down here, rather than calling apply force, hold on one second. So notice we have the same behavior we had before, but now we're just calling that cleaned up my main. Now, the other thing that I'm going to add is I'm going to add a thing that tells me how to draw this thing, whether it's thrusting or not. So to do that, I'm going to add a method up here, self dot is thrusting. Started out as false. But what I'm going to do is when I go to apply thrust, I'm going to say, hey, I'm going to apply the thrust, but I'm going to say self dot is thrusting equal true. So whenever I apply the thrust, it thrusts it. And then when after I draw the thing and I'm done drawing it, I'm going to set it back so it's no longer thrusting. So if they let off of it, it'll default back to, it'll draw it with the thrust shown, and then it will erase it right away. Now, how do I get it now to draw a thrust cone coming out of the back of that ship? So to do that, what I want to do, and actually let me move this to the top, up here. And here, what I'm going to do is I'm going to say if the ship is thrusting, so if self dot is so if it is thrusting, then here I want to draw the little thrust cone coming out of the back of it. So to do that, I'm going to do that similarly to how we did the points for this. So I want it to be coming out of the back end of the ship. So I'm going to just draw one point to start with. So here, essentially like, here, let's call this TX or TH. X, so thrust X, or let's say thrust point X equal. Now, this is going to be very similar to what we have down here, so I'm just going to actually copy these lines. And I'm going to move this up there, and this I'm going to make thrust PY. Now, when I do that though, right here, this 30, I'm going to have it be 30 units, but I'm going to have that be plus 180. So it's kind of come out the back of the ship. So that's going to give me that point coming out of the 30 units out of the back of the ship. And now I'm just going to draw that. So here I'm going to say pygame.draw.line. And I'm going to draw from the center of the ship, so self.x, well, let me draw this the right way, display surface, color, let's make it red, 255.00. And this is the 2 points, this is going to be self.x, self.y, those probably ought to be ints, so we don't have that dumb warning. And then the other point that this is going to be drawn to is going to be thrust x, or thrust px, thrust py. And those are already ints because we assigned them as ints up there. And now we want a width for that line. I don't know, let's just make it 3. And let's see what we get when we do that. Oops. Typo. All right, there we go. Now, that looks pretty dumb. It's just a red stick that comes out of the back of it. It looks more like a frog with a tongue sticking out. So I want it to be more like a thrust cone. So we could draw it as a triangle, I suppose. But the way I'm going to do this is rather than with one line, I'm going to want to have that and have it be static like it is. I want that line to be so it kind of moves around a little bit, so it has some randomness to it. So let's add that real quick. So up at the top, if I'm going to add randomness, I'm going to need to import random. And then down here, when I'm actually drawing that and computing that point, I want some randomness associated with 2 things. One is the length of that thrust thing. So let's do that. So thrust length equal, let's do random.randint. And let's say we want it to range between 30 and, I don't know, let's do 50. So that's one thing. So I'm going to take this thrust length, and I'm going to paste that in place of that and that. But the other thing that I want to do is I want to be able to also change the angle a little bit here. So this offset angle, rather than always being 180, I'm going to say thrust angle. So thrust angle. And up here, I'm going to do a randint. And rather than always saying 180 here, I'm going to say make it between 160 and, let's see, 200. Or in other words, one way you can think of this is 180 minus 20 and 180 plus 20. So in other words, this is a 40-degree spread on the thrust cone coming out of the back of that. And let's see how that looks. Okay, a little bit better, but it still looks kind of anemic. It looks kind of like a little tongue going blah, 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 more than it does a thrust cone. So to make that a thrust cone, I want to do a couple things. One thing I want to do is I'm going to add a little bit of additional color variation to that. And right now it's pretty much a solid red color. So I'm going to have thrust color there. And to compute the color of that, thrust color equal. Here's what it was before. I'm going to make this a little bit random. So random.randint. And we want it to be mostly red. So let's do, I don't know, like 180 to 255 for the red. And let's do for the green, we get yellows by having green mixed with that. So let's make this go, and let's go random.randint. Let's do 0 to 180. So we'll never have more green than we have red. So this should give us reds and oranges and yellows that come out of that. And let's see what that looks like. All right, so now we have some color variation going on our thrust flame, but it still isn't a cone. So how am I going to make that a cone? Well, one thing we might do is think, well, let's draw a bunch of those lines. So that's really easy to do. So I'm just going to do a for loop here. Let's say for I in range, and let's make let's make 30 of those. And that's 4. And let's just indent this stuff underneath there. So now we're doing 30 of those lines all on top of each other. And so that should be something that looks a little nicer. Now we have something that looks more like a thrust cone. And if we want, we could have more. We could notice we can play around with that effect any way we want in this code. We could say, you know what, I want a longer length. Let's make this 30 to 80. You know what, I want a wider angle spread. Rather than plus or minus 20, let's make it plus or minus 40. Now that might look a little bit dumb, but it definitely gives us something more like a flame effect. And if you wanted to, if we wanted to, we could actually do different lengths of lines in different stages. So we start off with the red and orange ones. We make shorter, or ones that are red that are the longest, shorter ones that are oranges and yellows, shorter ones that are mostly yellow, and then shorter ones that are in the white range. And then even shorter than that, we can make blues. We can make clusters of those that kind of overlap to have something that looks more like that flame that starts out white, hot, blue, and then works its way through yellow to orange to red as it builds up. We'd want to start with drawing the longer red ones first and layer the other ones on top. But you could have a pretty cool effect with that. We could also use the length of the line to change the color. It is too far, so I'm going to fix that real quick. So I think maybe 30 is good on this. The length is probably okay. Maybe it's a little bit too much of a thrust. Maybe drop this down to 20, 40. That looks a little nicer. All right, so there's our spaceship. Notice the force being applied to that, working just fine. And notice that apply force function we made. We could use that to not just apply a force like we have right now. So, but we could use that to apply a force for gravity to pull things down, or a force of an explosion pushing something away, or a force of a tractor beam sucking something in, a force of a collision making something bounce off of it. We have this generic apply force function now that we used to do that. And it's really just taking the motion vector, in other words, how this thing is moving, well, we also have no cap on the speed right now, so I can really accelerate this thing and get it to move really fast. It'll take a while to get it up to speed. And you'll notice we also don't have any friction. So again, Newton's law, it's going to keep moving at the rate it's moving at unless it's acted upon by a force. So let me see if I can slow this guy back down and get it to stop. Also, it helps to have sound effects. So all right, anyway. I know as much game code as I've written, and as simple as this is with a couple of triangles and some random lines, I still get a kick out of writing this code. It's magic. All right, almost got it stopped. That's hard to get it to completely stop. All right. All right, so let's go back to the presentation for a second. And you'll notice before we do that, the code, not a lot of code here. And notice how simple my main loop is. I basically say, hey, if they press A, rotate the ship counterclockwise. They press D, rotate it clockwise. They press W, thrust the ship. And then in my render part of that, you know what? Move the ship, render the ship, and then update the display. So listen, this is my main game code. Notice how simple that is, and that's because we put the logic and the math that's doing the stuff with the ship for rotating it or thrusting it into here. And notice that even the thrusting method is really simple. It says, hey, set the ship so that it's thrusting, and then apply the force. And really, if we wanted to, this applying the force, that could be done in our move. You could say, hey, if the ship is thrusting, apply the force to it. But we'll keep it like this for now. I don't want to go changing too many things. I'd probably do it a little bit differently if I was doing this for final code rather than demo code. But I think you get the idea of how this works. And to scroll through this, you'll notice it's really no new math. We're just using sine and cosine for both the displacements of the movement and the components of the motion vector, the components of the force vector, add them together to get the resultant vector, and then convert that new resultant vector back into a new speed and angle. And if you're taking the 1803 class, you're probably doing stuff similar with vectors. We don't even need to keep the speed and the angle of travel. We could just keep track of these vectors and be done with it, because the vector is really how it's moving. So we could really just say, hey, set the ship's motion vector to match this resultant that we computed, and that becomes a new vector without having to go to the speed and the angle, and then back from the speed and the angle, back to the vector, back from the vector, back to speed and angle. We're doing extra work here that we don't need to do. And if we're trying to make something more efficient, we could do that. And if I ever need the speed and the angle, that would be something we could always get this way rather than doing it every time we're applying a force or every time we're moving something. But that's more an optimization thing. What I want you to understand, have a working knowledge of, is how sine and cosine work to give you the components. The up and down component with sine, left and right component with x. We then scale that up based on the length of the hypotenuse, whether that's the speed or the amount of force. And then you can take one vector and another vector, add them together to get the resultant. That's what I want you to get out of the lecture today. Okay, let's go back to the presentation. Give me 1 second here. And I'm adding sound effects to that. All right, so let's, nope. There we go. All right, so we wrote our code. We did that. So that's all we're going to do today. A little over an hour today. So what I want you to do, or what I'd suggest you do, is play around with those things a little bit. And next class, we are going to have a lab that you're going to have to do. And we're going to play around a little more with some object-oriented programming for doing particle effects. So that's going to use sine, cosine. It's also we're going to use that to add gravity. So those sparks, when they come out, they kind of fall down like toward the ground, or smoke that gets kind of pulled upwards. So we're going to do particle effects next class. and we're going to be able to create some really cool effects from that. We're also going to look at using sine and cosine for some other things as well, other types of effects for how things move or how they behave. But we are going to have a lab 1 next class. So until then, try to get this code, the code that I wrote working, try to replicate that, make sure you understand it, study it. And other than that, stay safe, wear a mask if you're out and around other people that aren't part of your household, wash your hands if you go out and touch anything, and try to stay safe, keep everybody else safe as well. And that's it for today.